So a unit cell, right, has 6 parameters, 3 length parameters ABC and 3 angle parameters alpha, beta, gamma. So altogether we have 6 parameters for an unit cell. If these 6 parameters varies independently, okay, suppose A, B, C, they can be different, or they may be equal or 2 equal, right? Suppose if these parameters can vary independently, then okay, we expect 6 factorial different types of unit cells. Okay, so we expect 6 factorial unit cells. 6 factorial means 720 unit cells we expect if these parameters changes or varies independently. This is expected. Expected is 720, but out of these 720, I have told you in the last class that only 7 of them exist. Out of 720, only 7 exist, by assuming the unit cells are primitive unit cells. Okay, last class I told you primitive unit cell means if only corners of a unit cell are occupied, we call that unit cell as primitive unit cell. Okay, so primitive unit cell. What is meant by that? Okay, primitive means only corners are occupied. In a unit cell, if only corners are occupied, we call that unit cell as primitive unit cell or simple unit cell. Okay, by assuming only simple unit cell exists, right? Assuming only simple unit cell exists, people have identified 7 different types of unit cells exist in crystals. Whatever crystal in the nature you take, right? If the unit cells, if you assume the unit cells are only primitive, then right, out of 720, right, expected is 720, out of this only 7 different unit cells exist in nature. Therefore, scientists have given the term called 7 crystal system, right? So there are only 7 crystal system exists in the nature. Whatever crystal you take calcium carbonate, sodium chloride, whatever crystal you take, the crystal must belong to these 7 different types. But they made one assumption that only primitive unit cell exist. Okay, later what happened? What are the 7 different types? What are the 7 different types? Yes, yeah, these are all the 7 different types of unit cells. We call these 7 different types of unit cells or crystals as 7 crystal system. If any unit cell contain the length parameters all are equal and the angle parameters all are equal and it is equal to 90 degree, that crystal must contain cubic unit cell. In a unit cell, if A equal to B and not equal to C, alpha, beta, gamma are equal and it is equal to 90 degree, then that crystal must contain unit cell called tetragonal unit cell. We call that crystal as tetragonal crystal. The unit cell is called tetragonal unit cell. The crystal is called tetragonal crystal. Then we have orthorhombic, we have monoclinic, we have triclinic, we have rhombohedral, and we have hexagonal. Remember this order. I have given this mnemonic. Okay, CTO MTRH. CTO MTRH. C means cubic, T means tetragonal, O means orthorhombic, M means monoclinic, T triclinic or rhombohedral, X hexagonal. Okay, and I also told you clinic means non-90. Monoclinic means one of the angle is non-90. So out of the 3, one angle, see the alpha gamma are 90 degree, but one angle beta is not 90 degree. It is non-90. If all the 3 angles are non-90, it is called triclinic. Okay, so we have 7 different types of crystals by assuming unit cells are only primitive unit cells. But later, crystallographers, see the scientists who worked in crystal analysis, right? We call those people as crystallographers. Crystallographers, right? They found that non-primitive unit cells also exist in nature. Okay, non-primitive unit cells also exist, right? What are non-primitive unit cells? Non-primitive unit cell means, listen, they consist of particles. Non-primitive unit cell means they consist of particles occupy all the corners. Okay, also they occupy other positions in the unit cell. If particle occupy only corners, it is primitive. But in non-primitive unit cell, particle occupy all the corners. Okay, additionally, particle also occupy other positions in the unit cell. Okay, so in non-primitive unit cell, people have found three different non-primitive unit cells: body-centered unit cell, face-centered unit cell, and end-centered unit cell. Okay, so we have one primitive unit cell, we have three non-primitive unit cells, altogether we have four, right? Keeping these four unit cells in mind, people started to work on crystals, and they found that scientist Bravais, he found that 14 different types of unit cells exist in nature. Whatever crystal you take, right, that crystal must belong to any one of these 14 different types of unit cells. Okay, so crystals which possess or which belong to these 14 different types are called Bravais lattices. So we have 14 Bravais lattices. What are the 14 Bravais lattices? Let me discuss that. Before that, I'll introduce you what is this non-primitive unit cell. Body centered means, what is the meaning for body centered, what is the meaning for face centered, what is the meaning for end centered. Okay, I'll give this information, then we'll discuss about the Bravais lattices. Okay, yeah, so let me start. Okay, now so non-primitive unit cell, first let us start with the body centered unit cell. Body centered unit cell. What is mean by body centered unit cell? Listen, suppose listen, just for understanding purpose, I will take a cubic like unit cells, right? I have already told you, because it's a simple one to understand. Okay, so you take a cube, right? Now in the cube, all corners are occupied by atoms. All corners, let me represent here. So here I have one atom or a particle, here I have a particle, here I have another particle, another, here, another here, another here, another here, another here. You know very well, a cube has 8 corners. Okay, here all the 8 corners are occupied by particles. If only corners are occupied, it is primitive. But now we started to discuss non-primitive unit cells. Okay, in body-centered unit cell, out of this or apart from these 8 corner atoms or 8 corner particles, we have one particle at the middle of the cube. Okay, if one particle present at the middle of the cube along with the 8 corners, we call this type of unit cells as body-centered unit cell. Okay, so in body-centered unit cell, keep this in mind, 8 corner particles will be there, right? All the corners are occupied. Apart from that, we have one particle at the center. Okay, so this is called body-centered unit cell. In body-centered unit cell, we need to remember these informations. Students, keep this in mind. This is very important. See, in the case of a primitive unit cell, let me draw a primitive unit cell here. Primitive. I have told you in primitive unit cell only the corners are occupied. Okay, so only the corner are occupied by particles. Particles may be atoms, particles may be molecules, particles may be ions, right? You know that. So this is primitive or simple unit cell. Simple unit cell. Primitive is also called a simple unit cell. Look here carefully. Each corner atom, right, each corner atom is actually shared by 8 unit cells. You know very well in crystal, okay, many unit cells, right, combine together and form the crystal lattice, right? Crystal lattice என்றது நிறைய unit cells join பண்ணி form ஆவறதான் இல்லையா? So the corner of or the particle which is present at the corner of one unit cell, right, this is actually corner for 7 other unit cells. Okay, see, just for understanding purpose, let me show here. Let me just draw and show here what I'm trying to say. Let me just show you a crystal lattice like this. Yeah, see, I have shown a crystal lattice now. Actually, now this crystal lattice consists of 8 unit cells. Can you see the 8 unit cells, students?
Yes.
Are you able to understand the 8 unit cells here? Students?
Yes, sir.
Yeah, okay. Now listen, I'll take the middle point, okay, and I'll take one particle, I'll place one particle here. Now look this particle carefully. This particle or this point is not the corner for one unit cell, it is actually the corner for this particle is present at the corners of the 8 unit cells. Am I right? When you draw like this, if you take only one unit cell, yes, this particle is present at the one corner. But in the crystal lattice, this particle is not present only one corner of only one unit cell. It is actually present at the corners of the 7 unit cell. I'm sorry, 8 unit cells totally. Therefore, each particle present at the corner are shared by 8 unit cells. That's the point. Okay, so here in primitive unit cell, listen, this particle is not belong to only this unit cell. It is actually belong to totally 7 unit cells. Therefore, number of particles or number of atoms, suppose assume that these are all atoms, just for understanding purpose. Number of atoms or number of particles, let me write here, number of particles per unit cell. Per unit cell, how much? Number of particle per unit cell. See, remember, each particle is shared by 8 unit cell actually. Now, how many corners are there for a unit cell? We have 8 corners. So, number of corner atoms into each corner atom is shared by 8 unit cells. So, you have to multiply by 1 by 8. Okay. And how many corner atoms are there? In simple unit cell, we have 8 corner atoms. So, 8 into 1 by 8, you will get 1. Listen, if you see this unit cell, it appears that 8 particles are there. No. These 8 particles are not only belong to one unit cell, they are also shared to other unit cells. Therefore, what is the contribution of these 8 particles to one unit cell? This is what is called the number of particles per unit cell. To find this, what you have to do? First, identify number of corner atoms. Yes, we have 8 corner atoms here, or 8 particles here. Okay, particles present at the corner 8, and each corner particle is shared by 8 unit cells. Therefore, we have to multiply by 1 by 8, so that you will get the contribution of each particle to one unit cell. What is the contribution of one particle to one unit cell? That is 1 by 8. Okay, so 8 into 1 by 8 will give you 1. That means, right, these 8 particles contribute only 1 to the unit cell. Okay, it appears like there are 8 particles, but these 8 particles are also shared with other unit cell. Therefore, the contribution of 8 particles to one unit cell is actually 1. This is for primitive unit cell. Okay, and it is cubic type. Therefore, I'm using another, I'm going to introduce a word here, number of particles per unit cell of simple cubic. Simple cubic unit cell. Why I'm using the word cubic? Because I have taken cubic like unit cell. Number of particles, okay, per unit cell of simple cubic unit cell, or number of particles present in simple cubic unit cell, in one simple cubic unit cell is this. Okay, we call, listen, I'll write a term here, number of particles present per unit cell is called as rank. Okay, crystallographers use this term actually. Number of particles present per unit cell is called rank of the unit cell. So what is the rank of simple cubic unit cell? Why I am using the word cubic now? Because I have taken cubic type of unit cell. So what is the rank of cubic unit cell? Simple cubic?
1, sir.
That's all. Rank of simple cubic unit cell is equal to 1. Okay, right? Keep this in mind, very important. Similarly, we have to find out what is the rank for body centered unit cell, right? Yes, what's the rank for body centered unit cell? Shall we proceed? I'll write here. For body centered unit cell, what's the rank? Rank of body centered, is it cubic unit cell or not? Is this cubic unit cell or not?
Yes, sir.
Yeah, so I'm just introducing another term here, that is cubic, body centered cubic unit cell. Okay, BCC, rank of BCC unit cell, right? Yeah, we have, you just find out number of corner atoms, how many corner atoms are there, and each corner atom is shared by 8 unit cell, so you have to multiply 1 by 8, and number of body center atoms, NB, I'll put NB. What is NB? NB means number of body center atoms. Remember, if atoms present at the center of the unit cell, will that atom shared with other unit cell? Do they shared with other?
No, sir.
No. Therefore, if particle present at the center, those particles belong to only that unit cell. So now tell me, how many particles are there? How many corner atoms are there? Corner atoms.
8, sir.
8 corner atoms. Each corner atom is shared by 1 by 8 of the unit cells totally. And how many body center atoms are there?
1, sir.
1. So what's the answer?
2.
2. That's all. Okay. So for simple cubic unit cell, rank is 1. For body centered cubic unit cell, rank is 2. Rank means number of atoms per unit cell. Students, is this clear? Any doubt? Any doubt, students?
No doubt, sir.
Yeah, good. This is regarding body centered unit cell. Now let me go to the next one, that is face centered unit cell. Let me write here. Face centered unit cell. Okay. So we have discussed simple cubic unit cell. In the case of simple cubic unit cell, rank equal to 1. Then in the case of body centered cubic unit cell, okay, rank equal to 2. Okay. Now what about face centered unit cell? So the next one is face centered cubic unit cell. I am going to take cubic. Keep this in mind. This is very important. Don't think that, or don't make an assumption that only cubic unit cell exists. No. We have cubic unit cells, we have non-cubic unit cells also. Now cubic unit cell, it is easy to understand, that's all. Okay. As we go along, we are going to discuss non-cubic unit cells also. Okay, very specifically, if you write JEE examination or NEET, okay, you should know, right, other unit cells. Okay, yeah, we'll discuss that. That's not a problem. Yeah, face-centered cubic unit cell. Listen. Suppose I'll take a cube, face-centered cubic unit cell. Take a cube, right? Now I'll place atoms at the corners. See, just for understanding purpose, I'm using the word atoms. It need not be atom. It can be molecule. It can be ions. It can be anything. Okay. So all the corners are occupied, and you know very well, if only corners are occupied, we call that unit cell as simple cubic unit cell. What is meant by face-centered? Face-centered means, listen, a cube has 8 faces, right? I'm sorry, 6 faces. A cube has 6 faces. So if I place atoms at the center of each face, okay, so in this side face, I'll put one atom, and the top face I'll put one atom. In the bottom face I'll put one atom. In the left hand side face I'll put one atom here, and the front face and back side face I'll put atoms like this. Students, are you able to follow? If you take a cube has 6 faces, right? Now you place atoms at the center of each face. At the center of each face. Okay. So now listen, this is the arrangement of FCC unit cell. FCC unit cell has 8 corner atoms, right? And 6 face center atoms. 8 corner atoms and 6 face center atoms. This is called FCC unit cell. Shortly, we represent this as FCC. Okay. BCC means body centered cubic unit cell. SC means simple cubic unit cell. FCC means face centered cubic unit cell. This is the face centered cubic unit cell. Okay. Now, what is the rank? Rank of FCC unit cell, face centered cubic unit cell. Yeah. What's the rank? Listen, we have 8 corner atoms. So first you find out number of corner atoms and multiply by 1 by 8. Why we are multiplying by 1 by 8?
Because the corner atoms are shared by other 8 unit cells.
Yeah, each corner atom is shared by 8 unit cells totally. Therefore, we are multiplying by 1 by 8 because each atom will contribute only 1 by 8 part to one unit cell. Okay, that's why. Plus number of face center atom, I'll put NF. NF means number of face center atoms. Students, just imagine that if 2 rooms have common wall, if 2 rooms have one common wall, if you have an atom at the center of the wall, that atom is shared by 2 unit cells. Am I right? Are you able to follow? Yeah, very simple. Suppose I'll take, you just take, just look here. It's a very simple one. Okay. So now I'll place an atom here. This atom is present at the center of this face. Okay. Now I'll extend the lattice, and I'll draw another unit cell here. Another unit cell. Okay. Just imagine I have another unit cell. Now this face center. Okay, actually this face is actually face for this unit cell as well as this unit cell. Therefore, the face center atoms are shared by 2 unit cells. Am I right? It does not belong to only one unit cell because this face is the common face for both these unit cells. Right? Therefore, the atom present at the center, right, it is actually shared by 2 unit cells. So remember, in cubic unit cell, face center atoms are shared by 2 unit cells. Therefore, you have to multiply this NF 1 by 2. Why 1 by 2? Because each atom is shared by 2 unit cells. Therefore, contribution of the atom to one unit cell is 1 by 2. Okay. So now let me calculate. So number of corner atoms, yes, we have 8 corner atoms into 1 by 8. And how many face center atoms are there? Students, how many face center atoms are there?
sir.
6 face center atoms. Very good. 6 into 1 by 2. What's the answer?
4, sir.
4. Yes. Rank of FCC unit cell is 4. Rank of FCC unit cell is 4. Take down. Rank of FCC unit cell is 4. Okay. Then end centered unit cell, let me write here. Third type, end centered unit cell. End centered cubic unit cell. Let me write cubic. End centered cubic unit cell. I'm particularly interested on cubic unit cell, so that's why I'm using the word cubic. But keep this in mind, we also have non-cubic unit cells. Okay, yeah. So what is meant by end-centered cubic unit cell? Very simple. So I'll take an unit cell in cubical shape like this. Okay, we have atoms at the corners. I have an atom here. We have atoms at the corners. If atoms present only at the corners, then it is called simple cubic unit cell. Now, I am going to show you end-centered unit cell. For end-centered unit cell, you should place 2 atoms at the opposite face centers. I will place one atom in this face and another atom in the opposite face centers. Other faces should be empty. Okay, you should place only 2 atoms at the opposite face centers. Then we call this type of unit cell as end-centered cubic unit cell. End-centered cubic unit cell. Can you tell me the rank for this? Anyone? Rank of end-centered cubic unit cell, ECC. How many? Yeah, formula is this: corner atoms into 1 by 8, face center atoms into 1 by 2. Is there any body center atom? Is there any body center? No, no body center. So you need not include that. Yes, we have 8 corners into 1 by 8. We have 2 face center atom now into 1 by 2. So what's the answer?
2, sir.
2. That's all. Good. 2. So end-centered unit cell means in an unit cell all corners are occupied, suppose, and if 2 opposite face centers are occupied, we call those that type of unit cell as ECC, end-centered unit cell. Okay, so now let me just summarize. Right, everything. Listen. So we have discussed simple cubic unit cell. Okay, I'll write simply SC, simple cubic unit cell. Then body centered cubic unit cell. Then we discussed face centered cubic unit cell. Then finally end centered cubic unit cell. Yeah, what's the rank? Rank? Yes, students, what's the rank? Rank for simple cubic?
1, sir.
1. BCC? 2. FCC?
2, sir.
Good. FCC?
4, sir.
4. ECC?
2, sir.
2. Yes. Remember this information, very, very important and very easy to identify. Okay. See, here I have taken only cubic unit cell. Okay, but I told you we have non-cubic unit cells. So let me show you one non-cubic unit cell just for understanding purpose, which is very important for NEET and JEE examination. Okay, let me write that. Now let me show you a non-cubic unit cell in this category. Right? Let me take a hexagonal unit cell. Very specifically, I am going to take simple hexagonal unit cell. Simple hexagonal hexagonal unit cell. I am taking hexagonal unit cell, okay, not cubic, hexagonal. In the hexagonal type, simple means, listen, this is how the simple unit cell will look like. Let me draw here. This is how an hexagonal unit cell will appear like. Okay, it has how many faces are there, students? In hexagonal unit cell, how many faces are there?
8.
8. Very good. Yes. Out of these 8, 2 are one type and 6 are different type. What's that?
2 are hexagonal,
Very good. 2 are hexagonal face.
another is square.
Okay, square or rectangular like. Okay. Yeah, you're right. Yeah. So the top face and the bottom face, top face and bottom face, they appear like an hexagon, flat hexagon. Okay, and the remaining faces appear like a square or rectangular like. Okay, this is how an hexagonal unit cell will look like. How many corners are there? How many corners?
12, sir.
Well, very good. Yeah, there are 12 corners, right? There are 12 corner atoms. So if I place atoms at all the corners, okay, then if I place 3 more atoms at the center, students keep this in mind. I'll place 3 atoms at the center of the unit cell in a triangular manner like this. Okay, these 3 atoms are present like a triangle in the center of the unit cell. This unit cell is called simple unit cell. See, it consists of corner atoms as well as 3 atoms at the body center. Okay, this is the difference between cubic and hexagonal like unit cells. In cubic unit cell, we use the term simple if only corners are occupied. Whereas in hexagonal, simple hexagonal means corners plus 3 atoms at the body center. All together it is called simple. Okay, it is called simple hexagonal unit cell. Can you tell me rank for this? Anyone? Can you calculate rank? What is the rank of simple hexagonal unit cell? Rank of simple hexagonal unit cell. Yes, how to calculate? We have actually 12 corner atoms, right? So number of corner atoms into into what should we multiply? In the case of cube, each corner atom is shared by 8 unit cell. Whereas in the case of hexagonal unit cell, just join many hexagonal unit cell like this. Okay, by imagination you can identify. One atom is shared by, just join many hexagonal unit cells like this together. Okay, suppose
4, sir.
4. Okay. Let's try. See, I'll place one here. Okay, I have an hexagon here, another hexagon here. So this atom is shared by 3 unit cells, right? Here one, and here one come. Okay, so it is shared by 3 unit cell in the bottom. Similarly, you have 3 unit cells in the top, right? If you arrange many unit cells, okay, together, each corner atom is actually shared by 6 unit cells in the case of hexagonal unit cell. So remember, number of corner atoms into each corner atom is shared by 6 unit cell. Therefore, the contribution to one unit cell is 1 by 6. plus we have body center atoms plus phase center atoms, but there is no phase center atom, just for formula sake I'll write. Phase center atom, each phase center atom shared by 2 unit cell always. This is the formula. Yes? Can you tell me the answer now? Students? Can you find the answer now? We have 12 corner atoms, right? 6 above, 6 below, 12 corners. So 12 into 1 by 6. Plus we have 3 body center atoms, and I told you body center atoms are not shared by other unit cells. Okay, plus number of phase center atoms, there is no phase center atoms now, so 0 into 1 by 2. What's the answer?
Five.
Okay.
5.
Yeah. Am I doing any mistake? One second. Yeah. I made a mistake. I'm sorry. I made a mistake. Actually, I have to place 2 more atoms. I'm sorry. One atom at the top face and another atom at the bottom face. I'm very sorry. I forgot. This is the simple cubic unit, simple hexagonal unit cell. In simple hexagonal unit cell, all corners are occupied, and 3 atoms present at the body center in a triangular manner, and 2 atoms present at the face center of the hexagonal face. Face center of the hexagonal face. So top face is hexagonal, bottom face is hexagonal. So only the hexagonal faces are occupied by atoms. Okay, so I think this, now you put 2 here. So what's the answer now? I have 2 face center atoms. This is, remember student, this is simple hexagonal unit cell. 6. Yes, 6 is the answer. 6 is the answer. Students, keep this in mind. This unit cell is called simple hexagonal unit cell. Though the term look like the term is simple, don't think that only corners are occupied. Okay. In the case of cubic unit cell, it is correct. In the case of cubic unit cell, if only corners are occupied, we call that unit cell as simple cubic unit cell or simple unit cell. Whereas in hexagon, simple cubic unit cell consists of contains all the corners are occupied by atoms, then 3 particles present at the center, body center, and 2 present at the face center, right? Top, that is hexagonal face centers. So rank for simple hexagonal unit cell is 6. Okay, remember this, very important. Is it clear up to this? Any doubt, students?
No doubt.
Okay, ma, right. So now I'll go back to Bravais lattices. Bravais lattices. The scientist Bravais, he analyzed, okay, and he found that there are 14 different types of unit cells exist in nature. Okay, what he did was he took the 7 different types of crystal system, 2, 3, 4, 5, 6, 7. Okay, C, T, O, M, T, R, H. Remember this. Okay, C, T, O, M, T, R, H. Cubic crystals, then tetragonal crystals, then orthorhombic crystals, crystals, then monoclinic crystals, then triclinic, then rhombohedral, then hexagonal crystals, hexagonal. Okay, what Bravais did was uh, primitive, including primitive and non-primitive unit cells, right? He took all the different types of unit cells and started to analyze whether all the 4 different types, 1 primitive, 3 non-primitive, all the 4 different types exist in these crystal systems or not. He analyzed in this way, and he found that in cubic crystal only 3 exist. Okay, what are the 3? Simple cubic, body centered cubic unit cell, and face centered cubic unit cell. Only these 3 exist in cubic crystal system. Okay, then he analyzed tetragonal crystals, and he found that in tetragonal crystals, right, only 2 exist. Simple tetragonal unit cell, then simple tetragonal unit cell, then body centered tetragonal unit cell. Only 2 exist. In orthorhombic, he found that in orthorhombic 4 different types, all the 4 types exist in orthorhombic. Okay, simple orthorhombic unit cell, body centered orthorhombic unit cell, face centered orthorhombic, and end centered orthorhombic unit cells. All the 4 different types exist in orthorhombic crystals. Okay, then in monoclinic 2 different types exist. Okay, simple monoclinic crystals and end centered monoclinic crystals. Simple monoclinic, end centered monoclinic. These 2 exist in monoclinic crystals. Okay, and in triclinic, 1, in rhombohedral 1, in hexagonal also 1. Right? In triclinic, the one that is present is called simple triclinic. Here simple rhombohedral, here simple hexagonal. Simple rhombohedral, simple hexagonal. So what is the total, students? Just add these. What is the total? 14. Yes, these are the 14 different types of unit cells exist in nature. Whatever crystal you take in nature, okay, it must belong to these 14 different types. Okay, it must belong to any one of these 14 different types. Okay, so remember, in cubic crystal we have 3 unit cells, 3 different unit cells: simple cubic, body centered cubic, face centered cubic. Okay, mostly, right, in a NEET examination or JEE examination, if you see, right, they will ask only these 2. Okay, they won't go beyond this, right? So it is very important to remember cubic and hexagonal types. Okay, but questions will come from this. People ask question here, but we are going to discuss elaborately about cubic and hexagonal unit cells. Cubic crystal and hexagonal crystal. Right, students, up to this any doubt?
No doubt.
Okay, so remember, primitive means atoms. In the case of cubic crystal, primitive means atoms present only at the corner. Okay, in non-primitive we have 3 types: body center, face center, and end centered. Okay, but in cubic crystal we have only 3: simple cubic, body center cubic, and face center. Can you tell me what's the rank for simple cubic? Simple cubic, what's the rank? Students, what's the rank for simple cubic unit cell? 1. Very good. Rank for simple cubic 1. BCC? 2. FCC? 4. What about simple hexagonal? 6. Okay, remember all these things. Very important. Okay, take note. Okay, these different unit cells are called Bravais lattices. Bravais lattices. Right? Yeah. Now, Now we'll discuss some more points on these systems. So I'm going to discuss elaborately first about cubic crystals. Cubic crystals. Students, keep this in mind. We are going to discuss elaborately about cubic crystals and little bit about hexagonal crystals. We are not going to discuss orthorhombic, rhombohedral. We are going to discuss only these two, right? And very specifically, we are going to discuss elaborately about cubic crystals. Okay, right? How many different types of unit cell exist in cubic crystal, students? How many different types of unit cells exist in cubic crystals? Only 3, right? What are they? Simple cubic unit cell,
Body center.
body centered cubic unit cell, and
Face center.
that's all. Okay, in cubic we have only these 3: simple cubic, body centered cubic, and face centered cubic. So whatever cubic crystals you take, right, it must contain any one of these unit cell, simple cubic or BCC or FCC. Okay, now first I'll take a simple cubic unit cell, and I'll introduce some points here. So now you know what is rank. Okay, so first I'll take a simple cubic unit cell. Simple cubic unit cell. Okay, listen. While drawing simple cubic unit cell, we'll draw like this actually. Okay, we'll take a cube and we'll place atoms at the corners. Okay, let me show you. We'll draw a cube like this and we'll place the atoms at the corners. We'll place the atoms at the corners. This is how we draw. Yes, it is good at the beginning, right? For beginners, yes, we can start like this, but actually in the crystal they never appear like this. Okay, in crystal, how they appear? In crystal they actually touching each other, right? In simple cubic unit cell, see this, suppose I'll take this and this. Okay, this atom and this atom, these two atoms are actually touching each other. Okay, suppose if I take one atom, I will draw one atom like this and another atom like this. They are actually touching each other, but for understanding purpose we draw, okay, like this, and we'll say that it consists of 8 corner atoms and rank for this unit cell is 1, right? But in actual crystal, this corner atom and this corner atom, similarly all the 8 corner atoms are actually touching each other. So here I have taken only these two, these two atoms. Okay, listen, center of this atom and center of this atom, if we join them, that distance is what we call as the length parameter A. Length parameter A. Students, this is cubic unit cell, therefore A, B, C all are equal, right? Okay, so whether it is x-axis length or y-axis length or z-axis, whatever it is, it should be same. So I'll represent that as A. What is A? A is called the edge length. Edge length. A is called edge length. What is edge length is actually here? Listen, it is the radius of this atom plus the radius of this atom. Okay, so if this radius is r, suppose assume that the two atoms are similar atoms, same atoms. Okay, assume that all the 8 atoms are similar atoms. In that case, radius of this atom and radius of this atom are same. Therefore, I can write 2r equal to A. Is it correct? Students, is this
Yes,
correct?
sir.
2r equal to A, right? Or you can also write r is equal to A by 2. R is equal to A by 2, right? Radius of an atom is equal to edge length by 2. Edge length of the unit cell by 2. That is the relation between the radius and the edge length. Okay, keep this point in mind, very important. Then second information, what is the packing fraction of the unit cell? Packing fraction. Okay, let me calculate a quantity called packing fraction. Packing fraction of a unit cell is nothing but number of atoms, or I'll use the word like this, volume of I'm sorry, let me write here, packing fraction is equal to volume occupied by atoms, volume occupied by atoms in one unit cell, volume occupied by atoms in one unit cell divided by volume of the unit cell. What we calculate is actually volume fraction. We call it as packing fraction. So what is packing fraction? Listen, in one unit cell, how much volume is actually occupied by atoms? Okay, that should be in the numerator, divided by what is the total volume of the unit cell. So volume occupied by atoms divided by volume of the unit cell will give you packing fraction. So packing fraction is nothing but, what is packing fraction? Packing fraction is nothing but, it is the fraction of volume occupied by atoms in an unit cell. So what is packing fraction? Packing fraction means it is the fraction of volume occupied by the atoms in an unit cell. It is the fraction of volume occupied by the atoms in a unit cell. Okay, yeah, how to calculate this? See, in the case of simple cubic unit cell, you can calculate this by using this formula. Okay, what is the rank of simple cubic unit cell, students? What is the rank of simple cubic unit cell? 1, right? Yeah, listen. So volume occupied by atoms in one unit cell, listen. Volume occupied by atoms in one unit cell, let me write like this. Rank means number of atoms in one unit cell, number of atom per unit cell, into 4 by 3 pi r cube. What is this? 4 by 3 pi r cube, students?
Volume of sphere.
Yeah, it is the volume of sphere. Here it means volume of an atom. Volume of one atom into number of atoms. What will I get? Volume of one atom into number of atoms. Rank means number of atom per unit cell into volume of one atom. You will get total volume occupied by the atoms, correct? You will get total volume occupied by the atoms divided by volume of the unit cell. What type of unit cell we have now? What type of unit cell is this? Cubic. What is the formula for volume of a cube?
A cube.
A cube. Okay, here length is A, so A cube. Okay, so rank into 4 by 3 pi r cube divided by A cube will give you packing fraction, simple. And you know very well, for simple cubic unit cell, rank is 1. So you put 1 here, 1 into 4 by 3. So let me do it in the next page. I'll just turn the page. So packing fraction, let me write simply PF. Packing fraction equal to rank of the unit cell, which is 1 in the case of simple cubic unit cell, into 4 by 3 pi r cube divided by A cube. And you know very well, 4 by 3, I'll keep it as such. Pi is 22 by 7. Okay. R, what is the relation between R and A in the case of simple cubic unit cell?
R equal to A by 2.
R equal to A by 2. So I'll put R equal to A by 2 here, or you can do it the other way. You keep this R cube as such. What is A here? What is A? R equal to A by 2. What is A?
2R.
2R. So in the place of A, I'll put 2R. So here I have A cube. In the place of A, I'll put 2R. So I'll get 2R cube. 2R cube. So 4 by 3 times 22 by 7 into R cube by 8. 2 cube is 8. 8 R cube. This R cube cancel. Right? Can you tell me what is the answer for this? Use calculator and tell me. If you have calculator with you, you can use it and tell me the answer.
Eleven by 21.
No, I want the answer in fraction. Decimal சொல்லுங்க. Decimal point வச்சு.
0.52, sir.
0 point? Very good. 0.5? You're right. Tell me correct.
2. 0.52. 2, sir.
52. Then any more digit?
3.
0.523. Take. You can use calculator and you can find it out exactly. So this is the packing fraction of simple cubic unit cell. Okay? Or percentage packing fraction, which means you have to multiply this by 100, you will get 52.3 percentage. What is meant by that? What is meant by 52.3 percentage? If the total volume is 100%, out of 100%, only 52.3 is occupied. What about the remaining? In one cubic unit cell, only 52.3 percentage is occupied. What about the remaining? Remaining appears as empty space. Okay, it appears as empty space. So remember, in crystals we have empty space. This is very important. We call these empty spaces also as voids. Right? Yeah, we'll discuss that later. But keep this in mind. We have empty spaces. Right? This much is occupied. Remaining is empty. Empty space. Yeah. Next. Mute your mic, students. Mute your mic. Okay. So packing fraction is 52.3 in the case of simple cubic unit cell. Right? In a similar manner, we can calculate packing fraction for BCC and FCC. As I told you before, our focus is only on cubic crystals. Okay. So in cubic crystal, we have discussed simple cubic now. Okay. Now we'll start BCC. Okay. BCC or FCC, whatever it is. We'll discuss that one by one. First, let me take FCC, number 2, face-centered cubic unit cell, FCC unit cell. Face-centered cubic unit cell. In face-centered cubic unit cell, right, we draw a unit cell like this actually. Okay, in the beginning level, we draw like this. We'll place a cube and we'll place that atoms present at the corners. Right, all the corners, and all the face centers are occupied by atoms. The top face center, bottom face center, this side and this side, front, back, everything is occupied. Okay, all the face centers are occupied. This is how a face center cubic unit cell will look like. But students, keep this in mind. While drawing on a paper, you can draw like this. But in the actual crystal, right, these atoms, okay, appear close together, right? How actually they appear? Listen, I'll draw here. In the case of FCC, let me take the top face. Let me show the top face alone. In the top face, listen, you have the center atom, face center atom, and 3 other atoms are touching the face center atom like this. If you see from the top face, if you see from the top, it appears like this. These 4 are corner atoms, and the middle one is face center atom. This is how it appears in the crystal, actual crystal. Now the question is, do the corner atoms touch each other? See the appearance. Do the corner atoms touch each other? No, corner atoms are not touching, right? All corner atoms are touching the surface of the center atom. Okay. Now here what I'm going to do, I'll take this center and this center, join these two centers. Similarly join these two centers. Similarly join these two centers and join these two centers. Okay. So this is the top face. Top face will appear like a square. Okay. And this distance is what we call as A. A is nothing but edge length. Edge length. Now I'll take this center point as A, capital A, okay, and this center point as capital B. Okay, or you can take this center as B, this as C. Okay, the middle one is B. Middle one is B. Okay, see, let me show in a bigger spaces like that, so that it is easy to understand. Okay, so here I have a sphere and here I have a sphere. Okay, just showing the same appearance with the larger sizes. Now listen students, I'll take this center as A, this center as B, and this center as C. Okay, these three atoms are touching each other, right? Okay, these two atoms, that is A and C, are touching with the B. Now I'll join this A with the C. Okay, and this center, this length is what we call as edge length. Similarly, this is also edge length. This length is also edge length. Students, are you able to follow? Am I going faster?
No, sir.
Yeah. Listen, take the center of this corner and this corner, join them. Okay, if you join the corner atoms, that length is nothing but edge length. Now I am joining the centers of the diagonal atoms. That is this corner and the center atom and this corner atom. Okay, I am joining the centers of these. Okay, can you tell me what is AC here? AC, the length AC. Assuming all the atoms are similar atoms. Can I say it is 4R? 4 times the radius of atom? Is it correct? Because this atom has one radius R. Here this B atom has one radius here, one radius here, and for C atom we have one radius. So AC is supposed to be equal to 4R, right? Now this triangle, see this triangle this triangle, it looks like right angle triangle, am I right? It's a right angle triangle. So we can apply Pythagoras theorem, according to which AC square equal to hypotenuse. AC square equal to, I'll take this as say D. AC square equal to AD square plus DC square. Am I right, students?
DC.
Yeah. Yes. Now what I'm going to do, AC equal to square root of, what is the length AD? AD is nothing but edge length, which is A square. What is DC? DC is also edge length, which is also A square. So AC equal to root of 2A square. What is AC? AC is equal to 4R, we know. So 4R equal to root 2, I'll keep it as such. Root of A square is A. So 4R equal to root 2 into A. Or I can write A equal to 4R by root 2. 4R by root 2. Am I right, students? Are you able to follow? Up to this, any doubt?
No, sir.
Okay, right.
No, sir.